Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 is a multi-step question. So part 1 says how many valence electrons must be accounted for in the Lewis structure of chloroethane. And then step 2, consider the 4 resonating structures of phosphate. Calculate the average formal charge on a single oxygen atom, such as the one shown in blue, as it appears on all resonance structures. Express your answer numerically as a decimal or fraction. Okay, so let's do the first part of this question. I'll just call it A. We just need to draw the Lewis structure of chloroethane, which is C2H5. And they also just ask for how many valence electrons, so luckily we need to know the number of valence electrons to write the Lewis structure. So we can calculate it right now. Carbon has 4 valence electrons, and there are 2 carbon atoms, so we multiply this by 2. Hydrogen contains 1 valence electron, and there are 5 hydrogen atoms. And then the chlorine contains 7 valence electrons. So if we add these all up, we get a total of 20. So now the Lewis structure will contain the 2 carbons that have a single bond. And then I'm just going to draw 3 hydrogens singly bonded to one of the carbons. And then 2 hydrogens single bonded to the second carbon. And then finally, I'll draw my chlorine. So now notice my carbons and my hydrogens, they all have their full octet or doublet in the case of the hydrogen. And for chlorine, we just need to add all of its lone pairs. So if we count out how many electrons that are in this structure, each bond contains 2 bonding electrons. And we have 1, 2, 3, 4, 5, 6, 7 bonds, so that's 14. Plus the 6 valence electrons on the chlorine gives us our total valence electrons of 20. So that is part A. So now let's look at part B. They have 4 resonance structures of phosphate. And we want to calculate the average formal charge on just one of the single oxygen atoms, like the one in blue, as it appears on all of the resonance structures. So to calculate the average formal charge of the single oxygen, and it looks like I guess should be same, as this is equal to the total charge of oxygen divided by the number of oxygen atoms. So let's look at all of them actually. For all of the phosphate ions, the total charge of oxygen is -3. And if we count out how many oxygen atoms are in the phosphate ion, we have 4. So the average formal charge of oxygen on our phosphate ions is -3 over 4. So this is as a fraction, or we can write it as a decimal, -0.75. Okay, so now let's see what the junior tutor said. For the first part, valence electrons are outer shell electrons that are associated with an atom and that can participate in the formation of chemical bonds. So they have 20 valence electrons for fluoroethane. And for part 2, the average formal charge on each oxygen atom is equal to the total charge divided by the total entity of the oxygen atoms. That's the same as just how many oxygen atoms are in the compound. And they also got -0.75. So this solution is correct. Okay, so question number 2. What is the Lewis structure of hydrogen peroxide? So hydrogen peroxide has the chemical formula H2O2. So first let's find the total number of valence electrons for hydrogen peroxide. Hydrogen contains 1 valence electron, and there are 2 hydrogen atoms, so we multiply this by 2. And an oxygen atom contains 6 valence electrons, and we also multiply this by 2 to give us a total of 14 valence electrons. So now let's draw our 2 oxygens in the middle, and each of them will be singly bonded to a hydrogen atom. So now let's count out how many electrons I've drawn so far. So each bond contains 2 bonding electrons, and we have 3 bonds, so I have a total of 6 out of the 14. So I just need to write 8 more, electrons in my structure. So each of my oxygen atoms will have 4 valence electrons. And now I should have 14 valence electrons in my Lewis structure, and I can double check that everything has a full octet. So now let's see what the junior tutor said. Hydrogen peroxide is a chemical compound that is a pale blue liquid, slightly more viscous than water. It is the simplest peroxide and used as an oxidizer, bleaching agent, and antiseptic. It is unstable and slowly decomposes in the presence of light. So this is also why when you have a solution of hydrogen peroxide that you could buy at like a pharmacy, it's in a dark bottle. And this is exactly why, because it can slowly decompose in the presence of light. Oh, they said it right now. It's often stored with a stabilizer in a weakly acid solution in a dark colored bottle. It is found in biological systems, including the human body. Then they talk about how it is manufactured. It is interesting. And to draw the Lewis structure, we need to find the total number of valence electrons, which was 14. And they drew out the correct Lewis structure. So this solution is correct. Okay, so question number 3 says to draw the Lewis structures for A, B, C. So let's do the first compound. We first need to find the total number of valence electrons. So the silicon atom has 4 valence electrons. And fluorine contains 7. And since there are 4 fluorine atoms, we just multiply this by 4. And if we were to add these all up, we'd get a total of 32 valence electrons. So now let's just write our central atom. I can move over a bit. That is single bonded to our 4 fluorine atoms. And then I'm also going to draw in all of the lone pairs. Okay, so if we count out all the electrons I've drawn so far, we have a total of 32, and everything is satisfied in terms of having a full octet. So I know we have the correct Lewis structure. So now let's go on to our next compound. If we were to calculate the total valence electrons, selenium, I believe, contains 6 valence electrons. And chlorine contains 7. And we multiply this by 2 since there are 2 chlorine atoms. So 14 plus 6, we have 20 valence electrons. And selenium will be our central atom, and it'll just be single bonded to both of the chlorines. And each of the chlorines will have their lone pairs. So if we count out the electrons I have so far, we only have 16. So for the remaining 4, I'm just going to add them as lone pairs on the selenium. And now everything should have a full octet. And we have a neutral molecule and the right number of valence electrons. And now we need to do the last compound. And they gave us a hint that carbon would be the central atom, so that's good. So now let's calculate the total number of valence electrons. Carbon has 4, oxygen has 6, and fluorine has 7. And there are 2 fluorine atoms, so we just multiply this by 2. So if we add these all up, we get a total of 24 valence electrons. And now let's try to draw the structure. We have carbon as our central atom, and it's bonded to 2 fluorines and 1 oxygen. So let's see what happens if I draw in all of my lone pairs. Okay, so if we look at this structure, we'll notice that not only does oxygen contain a negative charge, but also our carbon doesn't have a full octet yet. So if I bring these electrons down to form a double bond, then we get the following structure, where carbon has a full octet and oxygen would then be neutral. And if we double check and counted out how many electrons are in the structure, then we would have our 24 electrons, So this is the correct Lewis structure for the COF2 molecule. Okay, so the junior tutor said for part A, first determine the total number of valence electrons, so they got 32. They have a plausible skeletal structure and wrote out all of the lone pairs and got the same Lewis structure I did, so that's correct. For the next molecule, 20 valence electrons, okay, so that's correct. And then for the last one, 24, and they have the double bonded oxygen. So this solution is correct. Okay, so question number 4. What are the Lewis structures that can be drawn with the compound formula C2H4O? So first let's count out how many valence electrons we should have in this molecule. So for the total number of valence electrons, carbon contains 4. And there's 2 carbon atoms, so let's multiply them by 2. Hydrogen has 1, and this will be multiplied by 4. And oxygen just contains 6. So this gives us a total of 18 valence electrons. So now let's try to write out some plausible structures for this formula. So we know that when we have just carbon, carbon, and then single bonds to the hydrogens, we know that we need to draw a double bond in there somewhere. So let me just show how if we were to draw our 4 or 3 hydrogens and an oxygen, then both of the carbons don't have a full octet, so they only both are attached, or they both only have 3 bonds attached to them. So if we draw a double bond, and if we show the lone pairs on the oxygen and count out how many electrons we have, each bond contains 2 bonding electrons, plus the 4 on the lone pairs on oxygen. This gives us our 18. So this can be a valid Lewis structure for compound with C2H4O. And we can also kind of experiment and draw out if a carbon was double bonded to an oxygen, and then draw out all the different hydrogens. Again, having the lone pair on the oxygen, this also gives us 18 valence electrons with the same formula. And then lastly, we could have kind of like an epoxide where the oxygen is singly bonded to 2 carbons, and then each of the carbons has 2 hydrogens. So this can also give 18 electrons with the same compound formula. And if we see what the junior tutor said, they said the same 3 structures. So this solution is correct. Okay, so question number 5. Give the full electron configuration for barium. Okay, so when we write out electron configuration, we want to follow the following rules. The first step is to divide your periodic table into different sections. So each section corresponds to a different orbital, S, P, D, and F. So it's important to know how to divide your periodic table this way, because sometimes on a test or like a quiz, they only give you just a blank, like a normal periodic table, and then you need to know what all the different sections or like where they would be. So for example, for our S block, it is the first two columns, including helium. So it's shown in light blue. So this is the S block. The P block is this whole like green rectangle. The D block is the middle transition metals, shown in orange. And then the F block are the last two rows, the lactanides and actinides in the periodic table. So that's the F block. And then step 2, so starting from hydrogen, you write the row number, then the block letter. And you kind of move from left to right across the periodic table until you get to your desired element. And then once we get to our D block, we're going to write the row number -1. And for the F block, it's going to be the row number -2. And I'm just going to add like a step 4. We typically order them from lowest to highest energy. So this basically is when you get to like your D block section. So if we were to go 4s and then 3d, sometimes it makes more sense to write your 3d and then your electrons before your 4s2 electrons, because realistically, your d orbitals that are half filled are more stable than a filled s orbital. So let me just write out our example, which I believe was barium. So for example, for barium, first let's locate it on the periodic table. So you can see it's right down here. So it has the atomic number 56, and we need to write the full electron configuration. So no shortcuts, or we don't write the shorthand configuration. Let's start from hydrogen and write the row number, which is 1, the block letter, which is S. And then to show how many electrons are in the orbital, we write it as a superscript. So 1s2 shows that there are 2 electrons in this 1s orbital. And then we go down to the next row, 2s, 2, and then we move across to 2p, which can house 6 electrons, and then 3s2, and then 3p6, moving down. I'm going to write my 4s2 first, and then moving across to the d orbital, we have 3d10. So you kind of count out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 all across the d orbital. 3d10. I don't even know if I can fit them all in this line. 4p6, 5s2, 4d10, and then 5p6. So barium is here. So then we just write 6s, and then up to the barium is just 6s2. Let me just try to fit it at the bottom on the right here. Should have given myself more room. But yeah, so this is the full electron configuration for barium. And if we wanted to write the shorthand configuration, basically all you need to do is find the noble gas that comes right before barium, which in this case would be xenon, and you just write it in square brackets. And then you continue on to write the rest of the electron configuration. So in this case, it would just be xenon 6s2. So it's much easier than writing the full electron configuration, but that's what the question asked for. So if we see what the junior tutor said, the atomic number of barium is 56. Yeah. And thus in this neutral atom, the number of electrons is also 56. With this, the corresponding electron configuration is 1s2, 2s2. Yep. 5p6, 6s2. Okay, so this solution is correct. Okay, so question 6. What is the electron configuration for the Cobalt 2 Plus Ion? So when we have ions which either have removed electrons or has like to an atom, or added electrons to an atom, then it has a charge. So when you have a plus charge, that means you removed electrons, and if you have a negative charge, that means you added electrons. So in the case of the cobalt, when it has a 2 plus charge, that means that we removed 2 electrons from a cobalt atom. So when we write the electron configuration of an ion, I first like to find out what the electron configuration is for just a neutral cobalt atom in its ground state, basically. So let's just find the electron configuration of cobalt in its ground state first. So you can find cobalt here, atomic number 27. So starting from hydrogen, we're going to move left to right, writing the row number and then the block letter. So we have 1s2, and the superscript tells us how many electrons are in that subshell. So we have 1s2, and then onto the next row, 2s2, then moving across the periodic table to the 2p, and then if you count it out, and you have 2p6, and then down to 3s, we write 3s2, and then 3p6, and then typically I like to sometimes write my my D block before my S block if it's around like the end, just to show that the electrons that are in the half-filled orbitals are more stable than if we had a filled 4s orbital. So I'm just going to write my 3d orbital first. And then from here, I'm going to count up to my cobalt. So if we count, we have 1, 2, 3, 4, 5, 6, 7. So I'm going to write 3d7. And then I'm going to write 4s2. Since the 4s orbital would be higher in energy than the 3d orbital. Okay, so we're left with this electron configuration for the cobalt in its ground state. If we were to write the Cobalt 2 Plus Ion, that means 2 of the electrons are removed. So we remove the 2 electrons that are in our s orbital. So now its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d7. And if we were to write the shorthand configuration of this, then you just need to find the noble gas that comes before cobalt, which would be argon, and you write it in square brackets, and then you just continue on writing the rest of your electron configuration. So in this case, it's just 3d7. Okay, so now let's see what the junior tutor said. A noble gas configuration of an atom consists of the elemental symbol of the last noble gas prior to that atom, followed by the configuration of the remaining electrons. Elements that are found in the last column of the periodic table are an important group of elements that are called noble gases. For example, sodium, which is element number 11. So they have an example of its electron configuration: 1s2, 2s2, 2p6, 3s1, wherein the first 10 electrons of the sodium ion atom are in the inner shell electrons, and the configuration of those 10 is exactly the same as the electron configuration of the element neon. This provides the basis for a shorthand notation for electron configurations, which is the noble gas configuration. For cobalt, a chemical element with an atomic number 27, it has a complete electron configuration of the following. This is the same as what I wrote as well. Hence, when we use the noble gas configuration principle, it can be shortened to argon 3d7 4s2. So when we have Cobalt 2 plus, it loses 2 electrons and becomes the Cobalt 2 ion. And they got argon 3d7. So this solution is correct. Question number 7. What is the full electron configuration of phosphorus 3 minus? So first let's find the electron configuration of just a ground state phosphorus ion atom. And starting from hydrogen, we're going to move left to right across the periodic table, writing the row number and then the block letter. So starting from hydrogen, we write 1s and then 2, which signifies that there are 2 electrons in this orbital. And then moving down to the next row is 2s2. Moving across to the p block, we write 2p6. So this 6 goes from boron to neon. And then we just do the same thing until we get to our phosphorus. So now to the next row is 3s2 and then 3p. And then we just count out all the electrons up to the phosphorus. So we count 1, 2, 3. So it just ends in 3p3. If phosphorus had a 3 plus charge, I believe, or was it 3 minus? Okay, so it was 3 minus. So if we have phosphorus 3 minus, that means it gained 3 negatively charged electrons. So our new electron configuration would start off the same. 3s2. And if we were to add 3 electrons, 1, 2, 3, we get 3p6. So now this tells us that this phosphorus that has 3 electrons added to it now has the same electron configuration as argon. On the other hand, when it was in its ground state, if we were to write the shorthand configuration, we would write the noble gas that came before it, which was neon. So we write neon in square brackets, and then we just continue on with the rest of the electron configuration. 3s2, and then 3p3. So originally it had the following configuration, but once it gained 3 electrons, it had the same electron configuration as argon, which is a noble gas. So the junior tutor said 1s2, 2s2, 2p6, 3s2, 3p6, which is correct. And then they explained why. An element's electron configuration is a numeric representation of its electron orbitals, which are regions around an atom's nucleus where electrons are likely to be located. It tells us how many electron orbitals an atom has, as well as the number of electrons in each of its orbitals. It shows the distribution of electrons of an atom. The area where the electrons orbit is called an electron shell. As an atom or molecule gains electrons, they fill different orbital sets according to a specific order. Each set of orbitals contain an even number of electrons when full, and the sets of orbitals are the s, which contains a single orbital, which can hold a max of 2 electrons. P orbital contains 3 and can hold a total of 6. The d orbital contains 5 and can hold 10 electrons. And the f orbital contains 7 and can hold 14 electrons. When writing the configuration, find the element's atomic number, and each atom has a specific number of electrons associated with it. So if it's neutral, then we have the same number of electrons as we do protons. Find it on the periodic table, determine the atom's charge, write the electron configuration notation. So they display the number of electrons in an atom as well as the number of electrons in each orbital, and they should be written in sequence, with the number of electrons in each orbital written in superscript to the orbital name. And then fill in the orbitals according to the number of electrons in the atom. Fill in the electron orbitals starting with the lowest energy, and then following Aufbau principle, Pauli exclusion principle, and Hund's rule, the phosphorus atom has 15 electrons, and the phosphorus ion has 18. The first 2 will go into 1s, the next 2 into 2s, the next 6 into 2p, and the next 2 and 3s. The last 6 go to the 3p. So this solution is correct. Okay, so what is the Lewis structure for disulfur dichloride? S2Cl2. So when writing the Lewis structure, we first need to find out the total number of valence electrons. In the case of the sulfur, sulfur has 6 valence electrons, and there are 2 sulfur atoms, so we multiply that by 2. And for chlorine, chlorine has 7 valence electrons, and we multiply that by 2 as well. And if we add it up, we get a total of 26 valence electrons. So sulfur is more, or is least electronegative than the chlorine, so I'm just going to write the 2 as our central atoms, each having a single bond to the chlorine. So now let's fill in all of the lone pairs on our terminal chlorine atoms. And let's count out how many I've drawn so far. So each bond contains 2 electrons, and we have 3 bonds, so that's 6, plus another 6 in the form of lone pairs on one chlorine, making it 12, plus another 6 from the second chlorine, so that's 18. So I need to write out 8 more electrons, and I'm just going to draw them in the form of lone pairs on my sulfur. Okay, so now we have our total of 26 valence electrons. And let's calculate the formal charge of our ions, of our atoms, sorry. So the equation for formal charge, this is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So let's do one of the chlorine atoms first. Chlorine contains 7 valence electrons. And if we count out all the non-bonding electrons on chlorine, then we count out 6. And there's a single bond to the chlorine, so there are 2 bonding electrons divided by 2. So all the chlorine atoms have a 0 formal charge. And then let's double check and do the same thing for sulfur. Sulfur has 6 valence electrons. The number of non-bonding electrons for both of them is only 4. And each of them has 2 bonds attached to it. So this is a total of 4 bonding electrons divided by 2. So 6 minus 4 minus 2 is also 0. So this gives us a neutral compound, which is expected. And the junior tutor said the same thing. So this solution is correct. Okay, so question 9 is to give the electron configuration of cadmium. So we can find the electron configuration of a certain atom just by following the set of steps. So step 1 is to divide your periodic table into the different orbitals or orbital sections. So for example, S, P, D, and F. And it's important to know how to do that. So our S block is the first 2 columns plus helium. The P block is shown in green. And the D block is the middle transition metals, shown in the orange. And the F block are the last 2 rows, which are the lactanides and actinides. So after we divide our periodic table into these different sections, we start from hydrogen. and we move left to right, writing the row number, then the block letter. And it's also important to note that once you get to the D block, it's going to be the row number -1. And once we get to the F block, it's going to be the row number -2. And we basically write our electron configuration from lowest to highest energy. Okay, so now let's do our example, which was cadmium. Yep, so just cadmium in its ground state. So that means no electrons were added or removed. It's just a neutral cadmium ion or atom. And then you want to find cadmium on the periodic table. So cadmium can be found here, atomic number 48. So when we write out the electron configuration, you start from hydrogen, and you write the row number and then the block letter, and then you just kind of go across until you get to your desired element. So we write 1s2, and then 2s2, and then 2p6, and then 3s2, and then 3p6. So these superscripts tells us how many electrons are in that subshell. And then we go down to 4s2, 3d10, 4p6. And then once we get to the row that contains the cadmium, since a half-filled orbital, a half-filled d orbital is more stable than a filled s orbital, we're going to write our 4d orbital first. So I'm going to write 4d and then count up to the cadmium, which is 10. And then I'm going to write my 5s2, which is higher in energy than the d orbital. So that is the following electron configuration. If I were to write this in the shorthand configuration, first I'm going to find the noble gas that comes before cadmium, which is the krypton, and then write it in square brackets. And then I'm just going to continue writing the remaining electron configuration, which is just 4d10 and then 5s2. Okay, so let's see what the junior tutor said. The atomic number of cadmium is 48, and given the neutral state of the atom, the number of its electrons is also equal to 48. Following electron configuration for this is the following: 2, 3d10, 4p6, and they have 5s2 first, but that's okay as well since we have a full d orbital anyways. So this solution is correct. Okay, so this concludes our session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed the video, you can give it a thumbs up and comment, or you can share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.